Okay. Now let's look at a very important concept in linear algebra. According to Gilbert's strength, this is one of the pillars of linear algebra. Four fundamental subspaces. Fundamental subspaces. What is one question you may have. So to be more precise, let's say this would be these are the four fundamental. Let me change the color. These are the four fundamental vector spaces associated with a linear transform. A RM%. So we've already seen last lecture that any linear transformations can be represented as a matrix. A composition of linear transformations is actually represented as a matrix. Okay. So whenever there's a linear transformation, there arises multiple vector spaces, right? The idea of linear transformation itself is to take a vector from one space to another. So whenever we are applying that transformation, we end up getting some vector space or subspace. So what are the fundamental subspaces associated with a particular matrix? First, spaces, a range space, or the column space. A part of this is actually obvious from the name, column space. So the range space of a matrix A is the set of all y's belonging to Rm. So we've already defined matrix A to be Rm cross n. All y's such that y is equal to Ax, and x belongs to Rn. We've already seen this. If whenever we were discussing about linear transformations, even before that, when we were discussing vector spaces, or linear combinations, to be precise. So linear combinations, which is a set of all linear combinations of a matrix A. Okay. So yeah, this is where did we discuss this? When we were discussing spans. Spans. We have a spanning set. What are the set of all combinations of those vectors, or the vectors in the spanning set? So if we have a matrix A, then a set of all y such that y is equal to Ax is the range space of that matrix A. So this is also same as the span of columns of A. So this is the linear transform way of looking at it. This is the vector way of looking at it. So what does that mean? We have a matrix A, which in fact have A1, A2, etc. AN. Is it AN or AM? N columns, right? N vectors. We can treat any matrix as, take each column of that matrix as a vector. So that we can treat them as n column vectors stacked together in a rectangular fashion. Then to take the linear combination of, or take the span of these vectors, uh, all the possible linear combinations, and that will be the column space. That's why it's called the column space. And column space is actually a subset of Rm. Why Rm? A set of all y's, right? Y actually belongs to Rm. So we're taking, whenever we are applying this linear transformation, this y is actually in Rm, x was actually in Rn. After the linear transformation, the vectors in Rn are taken to Rm. But is it the entire Rn? No, these are only the linear transformations. And it happens to be a subset of Rn. There could be other transformation which takes it to the other points in space as well. So a lot of the vector space is uncovered. Of the R m-dimensional space is uncovered with the linear transformation. We can't cover every space in the Rm dimensional space with these linear transformations, right? Hmm. Can we? Can we cover the entire Rm? How can we cover the entire Rm is another question. Okay, that's an important question to ask. Let me just note that as a side question. So it's a subset of Rm. How do we cover the entire Rm? Turns out we have to satisfy some conditions for that. Okay. This is a question which we have. How do we cover the entire Rm? We'll discuss about it later. This is an important question. So it's a proper subset of Rm. So let's say this is the Rm space, right? At least most parts of it, or some parts of it, is covered by the row space of it, where A is actually the transformation which takes a vector Rn to this Rm space, some vector. Okay, what about the remaining part of Rm? Can be covered? Or how can we say it's always, I mean, if RFA covers the entire space? For that, whether it covers the entire Rn or not, we have to look at the idea of something known as the null space. Let's discuss null space. This is also known as kernel. So all these spaces are defined in terms of a matrix A, null space of A, or it's also known as kernel of A, represented as kernel of A. Kerala, right? Kira. So this is the null space of A. How do you define a null space of A? Null space of A is set of all x's Rn. So here it was set of all y's in Rm. We're defining in terms of some linear transformation. Here also definition is in terms of linear transformation. But here y was actually the resultant of a linear transformation. But here we already know what the resultant of the linear transformation is. It's actually zero vector. The y is actually known. So there are some x's in Rn which when multiplied with A, it gives a zero vector. Basically, it takes anything, it cancels out something. Basically annihilates, even though we had a good, nice looking vector in Rn, multiplied with some x, I mean that vector with some A, the matrix A, then suddenly they got crushed into the singularity 0. So what are those vectors which when multiplied with A, it gets crushed to the singularity 0 in Rn dimension? So it's actually a subset of Rn. So the set of all such vectors makes a space. So is it a subspace? Of course, yes, because 0 is included, right? Yeah, the conditions also we have to check, but that's basically linear transformations always contain 0. It is scalable. Adding two zeros always gives you a 0, so it's a subspace. All those properties are satisfied, so it's a subspace, valid subspace. Then, if This is a set of such vectors, and mind you, it's a it's a subset of Rn. It's not a subset of Rm. You have to note that because these are the vectors which actually we have the set of input vectors, which when multiplied with a resultant was actually 0. So it's actually vectors which are initially in Rn dimension, not Rm dimension. Columns. Okay, let's write this. If columns of A are linearly independent, then null space of A is a null set. Oh, it's a not actually null set. To be precise, it only contains 0 vector. It's not a null set. Null set doesn't have anything in it, right? It's a singleton set which contains vector 0. So I think you might have got an idea here. So we had here the idea is we had an Rn dimensional space. And in the Rn dimensional space, we have many vectors, right? Which are living in Rn dimensional space. But some of them, subset of them, when multiplied with the matrix A, gets reduced to 0. This is basically null set of A. But there are the whole set of other vectors which are living in Rn, which does not hold this property. So what are those vectors? Yeah, we'll see them. We'll see them. Yes. We'll see them. Before that, there's another concept. So yeah, know this. Right now, earlier we have seen a partition of Rm space, right? Using the range space of A. But there's some part of it remaining, which is, but what are those vectors? Here we have seen another partition of Rn space. What is the other part which is actually not considered? So some part of it is a null space of A. What is the other part? Some portion is remaining here, some portion is remaining here. So to define them, we have to bring in another idea, which is change think, which is known as orthogonal complement subspace. So how do you define an orthogonal complement subspace? Given is equal to, we have a set of vectors AI belong to Rn, where I range from 1 to etc. We have n vectors. Each of them are m-dimensional. Let us assume that n is less than or equal to m for the time being. Then the orthogonal complement of the space is defined as set of all y's which is in Rm. So here note this. The vectors in S, they're all m-dimensional. The orthogonal complement vectors are also m-dimensional. They are a set of all such vectors which is defined such that phi transpose x is equal to 0 for all x belongs to S. So we have n vectors. X is one of those vectors which belongs to the set of S. You took that vector, you multiplied with another vector, and you got, it's not multiplication, it's dot product or the inner product. The generalized inner product. You took the dot product of it, then you got 0. The set of all such vectors is called the orthogonal complement subspace of that particular subspace S. So if you have an S, you can define an orthogonal complement set for that S. So it is a subspace We can prove this. The dimension of S orthogonal is greater than or equal to m minus n with equality holding if and only if a1, 2, etc. an are linearly independent. So we are in an m-dimensional space. We have n vectors, which is not exactly spanning the Rm space, but a subspace of it, S. Okay. So this can be viewed as something like this. We have an Rm space. Okay, it's better to represent them as squares. Why? Just because it's linear algebra. It's dealing with lines. You go with curves, then suddenly it doesn't make too much sense. Somehow we have an S. And how can we say we have an orthogonal complement? We have a set of vectors in S, and we have a set of vectors as or S complement or S perpendicular. This these vectors which are there in S, if they're linearly independent, if they are the n vectors, they span an n-dimensional space. But n is actually less than m in our case, this assumption. So what does the orthogonal complement space span? It spans an n minus dimensional space. This actually holds only since it's an orthogonal complement set. If it was not orthogonal complement, there would have been some overlap. This was not exactly some. There should have been some intersection, some overlap. So none of the vectors, can we span any of those vectors using these vectors? I mean, any of the vector which exists in S orthogonal, can we represent them using the vectors which are there in S? Interesting question, right? So I think the answer to that is no, you can't. You need a separate set of vectors. Whatever linear combinations you take them in S, it doesn't take you out of the space. You're always confined to the space. So whenever you have to represent a vector which is there in the orthogonal complement set of S, you have to use another set of vectors. Okay, that is a question which we can think about later as well. Can we represent any vector v which belongs to S using the spanning set of S? Answer is no, but we need to verify prove this. It's kind of an exercise. Okay. Okay, how do you look at examples which are orthogonal complements? Let's say S is equal to. Okay, another question. Is it the only case? What do you mean by that? What do I mean by that is, so if said we have a set of vectors, some of them span S and some span S complement. Then we have a vector in S complement, we can't use the basis of S to represent that. This is actually more like a what do you call it? Spanning set question, I would say. Anyways, so what is the peculiarity of these vectors? They are mutually orthogonal to each other, right? Right. So there's no, so it's not just dependence. They're definitely independent because they're orthogonal. Orthogonality implies independence. But they're orthogonal. What if they're just independent? Okay, we have a set of vectors. Set of all vectors in one subset is actually independent to a set of vectors another subset, a subspace. They could be mutually independent, not mutually orthogonal. Then how is this condition relaxed? Is this condition relaxed? Oh, or is it the exact partition? Does it require it to be orthogonal? In fact, it does not because we've already written this. Equality holds if they are just linearly independent. What are linearly independent? Okay. Oh, okay. So there is something which we I kind of messed up a little because see here independence is between the vectors in a particular subspace S. So what if the vectors are not they're mutually the vectors are there in two different subspaces S and S complement and they have this independence criterion. They are mutually independent. What do you mean they are mutually independent? How do you define it? More questions. What if okay, we can discuss this in some other lecture. What if they are just independent? What I mean here is vectors spanning S and S complement are if you stack them, if they put them together as a bigger set, like a super is equal to this. Let me call this as a spanning set of union sort of. They make this superset. How are they related? I'll think more about it and get back to you on this. Okay, let's move forward. Right. Yeah, let's look at a quick example here. S is equal to 1, 0, 0, 2, 3, 0, 3, 2, 0. This is S, which is an orthogonal set, is perpendicular, a span of 0, 0, 1. Why? We have a basis. Not that the third component is 0. So any kind of scaling and adding them together won't give you anything which is non-zero in the third dimension of this vector. So you have to span something in the third dimension. Let's say it's a z-axis. So we have to span the z-axis. We basically have to take something which is non-zero in that dimension. Not just that is enough, but it has to be 0 in the other directions also. So if I take the dot product between 0, 0, 1 and 1, 0, 0, it's 0, 0 vector. 0, 0, 1 and 2, 3, 0, it's again 0 vector. 3, 2, 0 and 0, it's again 0 vector. Right. Okay. So since we've defined orthogonal spaces here, we can now define the other two partitions which were missing earlier. So now let's discuss that. Let me number them so that, yeah. So we've looked at range space column or the column space of a matrix A. Look at null space of A, the kernel of A. Now we look at something which is known as row space. Which is actually the orthogonal complement of null space of. Remember, null space of A. What is the dimension? What is the dimension of null space? It's a partition. Okay. More accurate question is I mean, which all the vectors which actually spans null space of A. What are the dimensions of those vectors? They're Rn dimensional vectors, right? So so we've looked at the orthogonal complement of null space of A. So what will be the dimension of vectors which are actually spanning the row space? It's again Rn dimension. So that is something which you have to take care because it's an orthogonal complement of null space of A. How do we define this? So we've already seen for matrix A, whenever we are looking at the column space, these were the vectors, which are the column vectors of A. Similarly, we can also consider the row vectors. This is another way of viewing vectors. It's not necessary that we have to always stack the vectors along the columns of a matrix. We can also stack the matrices along the columns of a matrix, or we can view the rows of a matrix as vectors. But what will be the dimension of those vectors? Here, if we had an m cross n matrix, we had m such vectors, but the dimension of each vector was actually r each vector was actually rm, right? So here we have m such rows, but the dimension of each vector, each row vector, say B, C, is Rn. We have Rn dimensional vectors, n m such vectors stacked along the rows of matrix. How do you represent this in a more easier fashion? You can actually represent this as column vectors itself. You can use the same convention, but you have to just take the transpose. Because whenever you're taking the transpose, the rows will become the columns, right? So R of A transpose. So row space of A is actually, in fact, the column space of A transpose, or the range space of A transpose. So how you notate this is actually, denote this is actually R of A transpose is set of all y's which belongs to Rn, very important, which is Rn, not Rn, such that y is equal to A transpose X, that X belongs to Rn and is a subspace of Rn. So it's actually the span of rows of A. Okay. Now let's look at the fourth fundamental subspace. It is called the left null space. Some fundamental questions why. Okay, null space is understood because here right now we had some gap in null space, right? We had partitioned Rn. Some part of it was null space. Now we have a row space to cover the other partition. So we had earlier we had the range space of A. So some part of this is left. This could be some null space. In fact, it turns out this is actually the left null space. Null space understood, but by left. Okay, we'll see it. Just a convention. Left, right. Okay. So here the idea is this is actually a null space. What will that be associated with? It's actually associated with the uh, A transpose matrix. Orthogonal complement of the column space. Okay. This is the orthogonal complement of the column space denoted as R a orthogonal complement or null space of A transpose. How do we define that? Null space of A transpose as set of all x which is belong to Rm such that A transpose x is equal to 0. In fact, it's a subset of Rm dimension. So we've seen this is an orthogonal complement that so yeah, some things to note, some remarks. First thing is we had the range space RFA and its orthogonal complement is actually null space of A transpose or the left null space. So both partitions, the Rm dimensional space. So some part of it is actually RFA and some part of it is actually NFA transpose. Second, yeah, the range space we have already discussed is row space. This RFA transpose. Its orthogonal complement is N of A or the null space. So there are actually partitions are n-dimensional space. Some part of it is N of A, some part of it is RFA transpose. So we can do something like this. In fact, M is the dimension of. So this was, this was actually partitioning m-dimensional space, right? Range space and left null space. So since they are orthogonal complements. So we had Rm dimensional space. So dimension of Rm dimensional space is M. So M is actually dimension of R of A plus dimension of N of A transpose. Similarly, N, row space and null space actually partitions Rm space. As a dimension of R of A transpose is dimension of N of A. Can we say this? Yeah, we can say this. Why? Because they're complementary spaces. We've already seen this. One vector from the complementary space of another vector space can't can't be spanned by the vectors in the other space. So we have to basically add a dimension. If you have to add a dimension to it to bring in the new vector to it. Okay, so basically there is a subtraction of the dimension whenever we are talking in terms of orthogonal complements. This is an important thing. This is actually a thing which actually builds to something which is known as the rank nullity theorem. So when we discuss ranks, we'll discuss more about this. So right now we have discussed the four fundamental subspaces, about its dimensions, how they partition Rn and Rm space. Also, why left null space is called left. Okay. Let's say we have a transformation A on, okay, we have transformation Y just A times X. Let's say A is M cross N, X belongs to Rn, and Y belongs to Rm. So we initially had a vector X subspace. And next, it gets transformed. The X which is leaving in Rn, right? It's transformed to Rm after the linear transformation. This is Y. So in fact, this vector, what is the got transformed from n-dimensional space to n-dimensional space. But we also know these are not the entire set of vectors. We have a complementary subspace here. For Rm, what is this complementary subspace? What is this called? This is the range space of A. And what is this called? Null space of A transpose. Null space of A. And this is R of A transpose. Sorry, this is, yeah. Null space of A. Null space of A transpose. This is actually the left null space. This is actually the right null space. Seems like they end up being on the left and right side of the diagram. In the cross directions, not in opposite directions from how their names actually suggest them to be. Anyways, some weird naming. Fact. This is something which is like a representation of four fundamental subspaces. This is more nicely described in Professor Strang's lectures. And text. Okay, let's wrap this discussion here. The next discussion we'll discuss more on the rank of a matrix, and which is actually built from these concepts and rank nullity theorem and all those things. This is again another central idea in linear algebra.